Let me introduce the most often used symmetry operations. It's simple and illustrated on one example. The first symmetry operation we want to deal with is the so-called identity. The symbol for identity is E. We already introduced it. And as an example, let's look at the water molecule. So that's the Lewis structure of the water molecule. This is the bond between hydrogen and oxygen, and here this line and this line indicates the lone pairs, the electron lone pairs at the oxygen atom. Now let's do the identity symmetry operation with this molecule, and what is the result here? It's very easy to guess. It's exactly the same molecule. It's the identity, meaning we don't change anything, but that's to be expected for the identity operation, that we get the same molecule what went into that. The next symmetry operation I want to cover here is the rotation around two pi over n. And the symbol is Cn. And the n, what you see here, refers actually to this n, what we see here in this rotation angle. Now, let me explain this on an example. Let's again take our water molecule and see what happens if we perform a rotation. Let's first find the rotation axis. It looks like that we have a symmetry axis right here, meaning if we do a rotation around 180 degrees, then we would end up with exactly the same molecule. So 180 degree rotation. And 180 degrees, we know from our math lessons, is equal to pi. And when we now use our formula, what we end up is that 2 pi divided by pi is equal to 2. Which means if we apply a rotation by 180 degrees, we call the symmetry operation a C2 symmetry operation, or C2 rotation. And let's see what happens to our molecule. In order to show you what a C2 operation actually does, we give an index here. So let's say this hydrogen atom here is hydrogen atom 1, and this hydrogen atom here is hydrogen number 2. Let's draw again our water molecule, and now let's see what happens to these indices. Now a 180 degree rotation gives us H2 here and H1 here, meaning that the C2 symmetry operation gives us exactly the same molecule what went into this experiment, and the indices are just to show you what we actually did. But I mean, in reality, these two hydrogen atoms are exactly the same. Now let's move on to the next symmetry operation, which is the reflection. So number 3 is a reflection. And this one we write down with the Greek letter sigma. And also here, let's take a look at the water molecule and see what happens if we apply a reflection to it. So first, again, we need to find where is our reflection or mirror plane. In this case, we could make a mirror image of this molecule when this oxygen atom here is part of the mirror plane, meaning that whatever is on this side goes to that side and vice versa, and oxygen is within this mirror plane. Now let's see what happens. And also in this case, when we do this symmetry operation here, I want to make sure that you see what we are actually doing. So let's give this hydrogen atom number 1 and this hydrogen atom number 2. And after we apply the symmetry operation, and here in order to be precise, we actually do reflection with a mirror plane in vertical direction. So usually we give it a little index V for vertical. And the molecule, what we get from this symmetry operation is again exactly the same water molecule, except that this one is now hydrogen atom number 2 and this one is hydrogen atom number 1. And all we did is we exchanged the position of these two hydrogen atoms by using a mirror plane which goes through the oxygen atom. Symmetry operation number 4 is the so-called inversion. And the inversion we usually write down as I. So this time I can't use the water molecule because the water molecule does not have an inversion symmetry center. So let me take another one. Let's use carbon dioxide for this example. So that's the Lewis structure of carbon dioxide. You have the double bonds between oxygen and carbon here, and here you have two lone pairs on the oxygen. So you might ask, why is he drawing this molecule in this orientation? A very basic rule when you try to find out symmetry operations or later on also point groups is that whenever you draw a molecule, draw it in a way that the axis with the highest rotation symmetry points in vertical direction. Now, our rotation axis in this molecule goes in this direction, and here you can rotate the molecule as much or as little as you want. You will also always end up with the same molecule. For example, you can rotate it by 1 degree, you will end up with the same one. You can also rotate it by 180 degrees. It will always be the same. So that's why this one is the rotation axis with the highest symmetry. Later on we will see that this one we can call actually a C infinity axis. Now our inversion center is right here at the carbon atom. And now let's see what happens if we apply this inversion symmetry operation just around this carbon atom. So also here, in order to make sure that you know what I'm doing, let's give this oxygen atom a 1 and this oxygen atom number 2 as an index and see what happens. Okay, carbon won't change its place because that's the inversion center, so nothing will happen to the carbon atom. It stays where it is. But the oxygen atoms change their location. This one is now oxygen atom 1, and this one up here is oxygen atom number 2. Meaning, all we did is we exchanged the position of these two oxygen atoms when doing this inversion symmetry operation.